I could find out more papers.
Yep. All right, so I will bring the paper up. Work. Okay, so there were 2 articles posted on Frontier for today. One was about OCR, one was about augmented reality feature tracking, and Mimos prepared another one about the steganography, which she will start discussing now. So yeah, we will have the paper up there, but let's close that. How we managed to make that bigger before?
Shouldn't it be in the right corner at the bottom or something?
Yeah, that should be, but there is nothing.
Yeah.
Right. Right. Okay.
Okay, so today's topic is steganography on images using mobile phones. Steganography is the science or the art of hiding messages, files, images, or videos in other messages, files, or images, and which is used mainly for concealing information. The paper says that it is used for secure communication, although it's not the way to secure communication. It's just to exchange secrets that you don't want other people to see. Usually, the least significant bits in the file or the image are replaced with the hidden information, keeping the image visibly unchanged. So since it is visibly unchanged, people can't see the change, so it doesn't. They don't suspect that there is hidden information. So the main advantage that this technique has over cryptography, for example, is that when you see a encrypted file, you know that there is something hidden there and try to break the encryption. But here, it's like secrets hidden in plain sight. So since you don't suspect it, you don't try to find out. There are some important terms related to steganography, which is payload, the data that has to be concealed; carrier, which is the original file, which is used to hold the payload, carry the payload, and these together form a package, a stego file, or a covered message; the channel, which specifies the type of input, for example, is it a text file, a bitmap image, JPEG image, and so on. In this paper, steganography algorithms are used on microcontrollers and digital signal processing units, which are usually used in mobile phones. So even though the paper says that they use mobile phones, they don't. They only use microcontrollers, and yeah. In the related work section, they talk about other work and where this is applied. So steganography is mainly used in digital watermarking to protect intellectual property rights. So authors of files can watermark their details on files. So if somebody is using them illegally, then they can find out. For generating secure communication over public telephone network, although I don't know how that would work. If you have to record the audio first and then analyze, and also to send images via SMS, which has some limitations since the size of SMS is small and the image has to be black and white. In the tests and results section, they tell that high computational digital signal processors are being used in mobile phones, which also use multi-core architectures. Information that is usually exchanged by phones is text, files, images, audio, and video. And steganography can be used in all of them. In this paper, they use steganography to exchange images. So they want to hide images inside of other images. No. Yeah. So the first image is the carrier, the original image, which we use to carry the second image, and they are put together in C. So you can see it at all. There's a clock in the book somewhere in C, and then you extract the image. They are using 3 hosts for this experiment, an ARM microcontroller, 60 megahertz clock and RISC architecture, multi-core processor, which is called ISAC, which is a graphic processing unit that has specialized unit for signal and image processing, 200 megahertz clock, which is adjusted to 60 in order to be comparable to the ARM, and a personal computer, for which they don't give any details. They say that they had challenges because each of the platforms has its own characteristics. For example, the ARM has a pipeline unit but doesn't have any special signal and image processing units. And the ISAC is performing very high, but the algorithms need to be adjusted so that they can be used in parallel execution because it's a multi-core processor. And they use 3 steganographic algorithms, LSB, which is the least significant bit. So the least significant bits in the carrier are replaced by the most significant bits in the payload. So in the clock, when they extract, they only get the most significant bits of. So D is only the most significant bits of B. Because they only take the most significant bits of B and put it inside.
So you were losing some information, some details.
So you don't get the full image.
As you can see. And there is a bit of a spillover of the carrier image into the image, like you see here it is clean, but here you can see some of the spillover.
Yeah, and this algorithm, the LSB, the significant bit, uses RGB images. And then the second, the YUV, is converting the RGB images to YUV, which is another color space. And then the LSB is applied. And then they have the Karhunen-Loewe transform, which also uses the LSB but hides the parameters of this transform inside of the image and not the colors. It doesn't change the colors of the image. Then they have the data analysis in tables. So they're analyzing first the replacement of 2 least significant bits with 2 most significant bits for each of the platforms. And we can see that the PC is doing very bad, but it doesn't say anything about the PC. It doesn't anything at all. And usually when we compare the speed of algorithms, we have to know under what conditions they're working. So, and the ISAC is doing best.
Yeah.
But mobile phones don't really don't have that.
Have that,
I
yeah.
think.
They're based on the
They-
ARM architecture,
yeah.
but they don't have that special processing unit.
Yeah. Then they tried to do the LSB with the 4 bits and see that there's very little change in the speed. So similar.
Mm-hmm.
So they can also do this for a similar amount of time with 4 bits.
And also the ISAC is
Mm.
beating the other one by a
Yes.
huge factor.
Yeah, and then in the third table, they're using the second algorithm, and this always ISAC wins. And you can see it also from the graphs, the results, that the PC is doing very bad.
Mm-hmm.
The difference is huge between the PC and the 2 others. And then basically the conclusion is that the best is the ISAC, and the best algorithm is the Karhunen-Löwe transform, and nothing else.
Do they establish the quality, like why the Karhunen-Löwe transform
No.
is the best?
Just based on these results. The
Mhm.
paper wasn't really good, but only the concept seemed interesting. And this is actually only the decoding time.
Mm-hmm.
If you want to decode the image, then this is in the tables, that's the time for decoding.
Mm-hmm.
And what I also found interesting is the precision. Like the speed is 25 milliseconds, and just 25, not 25
With no
point
error.
something. Yeah, no error, nothing. It's very precise for an algorithm.
And no decimal
25.
places.
I expected a floating number or something.
Yes. So that's a little bit suspicious.
Yeah. And they didn't have a hypothesis from the beginning, so they were just describing their work.
Mm-hmm.
The algorithms are not tested in real phones, so they're just using ARM and ISAC. So testing is directly on microprocessors, but if they were inside a phone, those microprocessors would be used by different processes at the same time. So
Mm-hmm.
I don't know if the results can be generalized
Mm-hmm.
for the mobile phone case. So
Yeah. So if you're rounding, then the numbers you have to mention in text that the results were rounded to the most significant digit or whatever. So same here. It is obvious that they kind of rounding to 2 decimal places most of the results, but here they kind of rounded it to the units.
and there's also some content from Wikipedia I read.
Mm-hmm.
So it seems like they don't reference it. It seems like Wikipedia
copied
is
it?
common knowledge.
So you should not do that. So if you're copying stuff from Wikipedia, you have to quote it or reference it.
Yeah, but when you reference Wikipedia, then that's not good. So
No. So you
shouldn't
usually should
reference.
find the source.
Yeah.
Yeah. What if you wrote your own Wikipedia entry? Can you copy and paste it? If it's yours. What do you think?
Is it yours if you write it?
Yeah, you wrote it. You wrote, let's say you defined something on Wikipedia, and then in the article you kind of wrote the same thing again.
You have to reference it.
Who should reference it? So Wikipedia should reference your article, or your article should reference the Wikipedia?
Yeah. Yes.
Yes.
Depends what you write first.
Yeah.
If you write the Wikipedia page first, you should reference to the Wikipedia page.
Yeah. Yeah, the thing with Wikipedia is that it's a living document. So your paragraph will be edited and it will change after a while, right? So even though you might have written that first and article second, it kind of makes more sense to reference the article from Wikipedia, because that paragraph is going to be edited and it will not be the same after a few years. Have you added something to Wikipedia before? Yep. So you know the process. You propose the changes, and then other people have to approve it, and they can modify it as well. And you have a history of things that you wrote and things that were changed as well. There is a log of what has happened during the discussion. So when I was doing my PhD, I was contributing to some of the Wikipedia pages at the same time as writing my thesis. And because it was about virtual machines and was kind of the same topic, so I ended up using some of the phrases which are on Wikipedia, which are mine, without referencing it, because I wrote it sort of at the same time. Yeah. Because you kind of, as Mimosa said, you're not supposed to really reference Wikipedia for two reasons. One reason is that it's not really authoritative kind of source of information.
Everyone can write.
Anyone can write stuff there. And second thing, it's that it's a living document. So something that you've referenced this year, in 2 years' time might be completely different, or the page might be rewritten and changed, and you're sort of referencing something which is not there anymore, or is different.
I only use Wiki when I reference is only to explain definitions or terms that are like.
Yeah, so you should use textbooks for that.
Yeah.
So usually you should find a source which is a kind of a seminal textbook in the field, or All right,
mostly use the citation at the bottom of the Wikipedia
to find those. Exactly. Yeah, you can use Wikipedia to find those references. So what do you like about the paper, and what you don't like?
It's badly written, and it's not. I don't know. It's not very serious work. But the concept is interesting. That they try to analyze different algorithms and in different platforms.
Mm-hmm.
That was interesting.
Mm-hmm.
But otherwise, Wikipedia and shouldn't be doing that. And the charts, for example, it just says execution time and no unit or anything. Image size, numbers, but not bytes or
points or pixels or what is that? Yes.
nothing.
So it's a little bit sloppy.
Yeah.
Is the methodology okay? So if you want to showcase something that can be done on mobile phones and you actually didn't use mobile phones, you use the microcontrollers, microprocessors directly. Is it a valid methodology?
I don't know. Maybe it's better to. I don't know exactly if it's better, because if you do it like this, then you can say this algorithm uses this exact time, because it's only doing this process at the time.
Yeah, so it's sort of the optimistic setup.
And if you integrate, then you have to know what conditions there are in the mobile phone or in the PC.
That's right.
At that moment, and it can't be generalized to other conditions.
That's right.
So I don't know which one would be better, because they're usually always integrated. If you want to use it on a mobile phone, you have the ARM in the mobile phone. You don't do it separately.
Yeah. So, I mean, it is a good, valid methodology. You can measure performance this way, in isolation, using kind of idealized conditions, because then it's easier to compare two algorithms, because they, as Mimosa said, that's the only thing which runs there. Often people also use emulators. So they have a PC setup and they use emulator of particular architecture like ARM or something else, and they count the clock cycles and they compare performance using those counters. So they don't run it on the actual hardware, then run it on the emulator and count how many clock cycles particular architecture used, and then by multiplying it by the clock rate of a particular CPU, you can estimate what would run faster or slower on wall clock time. And it provides you an opportunity to constrain the setup, so then you don't need to deal with some of the external variables, which you would if you are running it on the real phone.
So the good thing also was that they adjusted the ISAC to 16 megahertz, the clock, so the results are comparable, not just one is doing better because of the clock.
That's true.
They normalize both at 60 megahertz.
Yeah, that's true.
But I miss detail for the computer. Doesn't say anything. For
No.
the 2 is kind of.
So it is surprising that the PC loses the battle with the other microcontrollers, because normally that's the other way around.
Yes.
So normally if you're comparing anything on the phone or ARM to an Intel CPU, the Intel CPU always wins. It's more grunty, faster, bigger. Yeah, so it seems like they try to kind of unify it so you can compare apples with apples, but it's hard. So even reducing the clock rate, it is somewhat questionable, because even if you're comparing those two architectures with being clocked at the same clock rate, what does it mean? Does it mean they generate the same amount of heat? So you're kind of comparing per wattage of how much you can compute in what time. So it is a little bit difficult. So usually we try to compare it either with the wall clock, so in terms of raw performance, how fast certain things work, and then how much energy they consume. So you know how much it costs to compute certain thing with particular speed, right? But just doing the comparison they've done, you still don't know the answer to that question. You still don't know if the per wattage is the same or the cost is the same, even though they try to unify the clock cycles. Those articles are something that you probably will deal with, this type of articles, because of the projects that you're doing. So it's sort of a typical case where you're developing something, estimating the performance of it, comparing to existing methods, and then showcasing how it works. So yeah, some of the strengths of this methodology are good to kind of look at, and some of the weaknesses are, you try to avoid. So how can you, so let's say you do have a watermarked material. Let's say you have a photo which has some watermarking. How can you de-watermark it?
You have to know the algorithm they used.
Yeah, can compressing and decompressing it, would it help?
No, in finding it? In finding the
No,
watermark?
in destroying it.
Probably, I don't know.
It could. It
Yeah.
depends on the algorithm. So there are some algorithms which work
Because
with compressed
algorithms
images.
Throw away.
Yeah.
So,
Yeah. And then with detection, if you don't know exactly the algorithm, it's really hard to find it. And the image appears to be, especially the random generated images, they seem to not contain any information, because no matter what statistical analysis you use on the image, it appears random, but it will have one or two hidden images within itself, and you need to know the key to decipher it. Even if you know the algorithm, you still need to have the key. It's sort of the same principle. So where would you use it? Would you use it yourself? Do you have the need to communicate securely with anyone?
The only one I could think of would be banks and insurance companies. potentially, but
Yeah. What else?
Spies.
Yeah.
Terrorists.
Terrorists. Yeah. What else?
Oh yeah. Gee, mistress.
So one of the areas which we talked about in last week was reality games. Would you be able to think of some examples of using it in some sort of reality game?
if one have a geoposition of some sort, one could post posters with hidden watermarks of sorts,
Yeah, that's
which
right.
only viewable through the application.
Yeah, that's right. So you could hide some images and some information or some messages to players of particular team in visible objects, which everybody can see, but not everybody can get that hidden information. So you could design some scenarios using this technology for the gameplay. So not necessarily a very serious use cases, but fun as well could be used. Could be useful for fun
So maybe
activities.
you can do that at school. Actually, you can have the result in the exam, and if you can solve the problem, you get the result immediately. Because you can use the phone and make a program to analyze to get the answer.
Yeah, yeah.
Well, that's cool.
Yeah, it could be used for augmented reality as well. So you could imagine you have some augmented reality glasses, and you can see things that they are there in plain sight, but you need to decipher them. Yeah. Right, so yeah, we talked about the images being kind of visible like this, or you can have a substrate which is completely random as well, right? So you can have images which just look like noise. They look like white noise, and they have information within itself. So do you know TrueCrypt?
You call it what?
TrueCrypt.
I've heard the word.
So the TrueCrypt is an interesting piece of technology. So you know about encrypted volumes. So you can have a hard drive, and most of the external hard drives now come with the encryptor, right? So you come up with the key, some sort of a passphrase, and then you enter the passphrase, and the information on the disk is mangled in such a way that you can't read it unless you decipher it with the passphrase that you know, right? So TrueCrypt works like that as well. It creates a volume, disk volume. It can be a disk image, or it can be a physical volume on your hard drive, and you can store information there. But the problem is that the court can force you to reveal the passphrase. So if you have a hard drive and the court thinks you're doing something illegal, they can order you to reveal what the passphrase is to decipher the disk, right? So then you have to tell them the passphrase, and they will decipher the disk and see what's inside. So TrueCrypt has a different mechanism. It has two volumes. So it occupies the entire disk space and then sets a small part of it to be encrypted in a normal fashion, and the rest of the disk space is encrypted with a different passphrase, and it's invisible, right? So when you store information on the hidden partition, it's stored there and encrypted, and you have the other part, which is just kind of like a dummy partition there. And then the whole image is encrypted. And then if the court decides that they want to see what's on the disk, then they force you to reveal the passphrase. You reveal them the passphrase for that small volume which you have some files on, and they decipher it. They get access to those files, and then the rest of the disk appears as white noise, right? So it's impossible to verify that there is anything else on that disk apart from the volume they deciphered. And they can't tell the difference. There is no mathematical way of telling if this white noise has anything or it doesn't. And you don't ever need to reveal the other passphrase because you can continue claiming that there is nothing in there, that you don't have that hidden partition. Because TrueCrypt has two modes of working, either as a normal volume or as this dual volume. So it's very controversial because now you can truly hide something, right? And the court can't tell you to reveal it because they can't prove that there is anything there. If you have encrypted volume, they can prove that there is an encrypted volume and there is information there, and you have to reveal the passphrase. But with TrueCrypt, there is no mathematical way to tell the difference between information which is there or which isn't, right? So last year, TrueCrypt stopped developing the product without giving a reason. So they say, well, sorry, we can't, continue maintaining this piece of software, and we will not maintain any new versions, and they backed off without giving any reasons. And there were a lot of theories why that happened. And one of the most possible one was that, American government decided that that's a project they don't want to continue having. So there are a couple of forks, and the code was forked, and the code base was also checked if there are any backdoors to the software, and there seem not to be any backdoors. So there was another theory suggesting that NSA actually wanted a backdoor in the software, and they killed the project because the developers refused to have a backdoor to the system. So they said, well, we can't have the backdoor, therefore we're gonna quit instead of having a backdoor in that product. So there are a couple of versions which you can still download, and those versions are verified, and there is no backdoor in those versions. But yeah, if you need to hide some information, it's kind of technically possible, and it's technically not possible for anyone to tell that there is hidden information there. So it's sort of similar to steganography, because you have some information which is there, but it is part of that kind of white noise, and it's statistically impossible to tell the difference. So that's another use of this technique, but not necessary for image. So you can store images, and you can store other things inside the image. You can store text as well, right? So they've used hiding additional images inside the images, but there are other digital information that you can store. So one use case for this technology is for child pornography, to exchange images illegally using this kind of technique as well, right? So that is used for, exchanging images that are not normally visible. So a lot of forensic checks are basically running through scans of images and trying to work out if there are other images hidden in the existing images. So a lot of digital forensic software has kind of toolkits and some of those algorithms to kind of try to brute force and try to find out if there is potentially information hidden in the steganographic images. Yeah, so that's another. Right. Any other ideas or questions about the paper? Okay, so thank you. If you want to talk a little bit about the OCR and maybe mention what you've done last semester for the OCR project, that would be great. You don't need to discuss the paper. Yeah, just improvise a little bit. So what is OCR?
Optical character recognition.
You all know what OCR is? What is it for?
To recognize characters from the picture, image,
Yep,
change it into text,
yep.
and then you can use the text later.
That's right. So once we know what the text is, you can do semantic analysis on the text. You can do something with the text, which you can't really do with the image. So if you have an image of a page with letters, you don't know what it is all about, and you can't query, then you cannot do a lot of useful things. If you know that this page with this text has this actual text in a text format, you can do queries and you can do search on the text, and it becomes much more useful. So for scanning documents, for retrieval, for search, for generating metadata about documents, for scanning old books and making them searchable, yeah, OCR is great. Also for some of the user interfaces for disabled people, for vision impaired people, that's useful too. So what have you done last year?
Last semester we had to build an OCR, take pictures in different lighting conditions, and then read the text, and then do machine learning, like separate every character and teach the machine. This is an A and this is a B and so on. And for example, this paper goes through some of the steps, but you have the paper?
Yeah, I'm just about to click on it.
So they say that the algorithm works for different lighting conditions, but then it doesn't. So they have different lighting conditions. Like almost the end. This one, the next one. Yeah, so they're kind of different, even though not so much. The
Right.
lighting conditions, but if you see the next, the right, no, just on the right, they can't read those letters. So it doesn't really work. They have tried to use it on different lighting conditions, but it doesn't work on different lighting conditions. And OCR is about turning the text which we take a picture of into machine text. And then they don't go to that step. They just recognize the text, but don't.
That there is text.
Yeah,
Yeah.
they know. For example, we had problems with recognizing the letter I, because it didn't know if it was an I or an L, or with O's and zeros. So OCR doesn't work. You can say that this method really works if you don't see the result.
No.
If you don't see that is multipix, right? If it is machine text, if it returns multipix in the end or something else. So I don't know if this method really works if I don't see that result in the end.
That's right. So there are some characters which even confuse even the human readers, right? So the I and L's and zeros and O's. I don't know how many times you had that problem, but
we were taking pictures of Norwegian text, and then it was recognizing the like as A and E separately. It was dividing it in the middle.
Those two, yeah.
Yeah.
Norwegian is extremely complicated because of those characters. Yeah, makes it harder.
Yeah, and the title says a lightweight text image processing method, but they don't give any performance result, and they don't show that it is lightweight.
Yeah.
I think they have only one sentence in the end that says something about the lightweightness, but not much. Yeah, as an example, the whole pipeline runs in a fraction of a second. So that's not good.
That's a very solid scientific statement.
And uses little over 1 megabyte of working memory. Little, okay. So
Yeah. So there are some problems, but what do you think is different on doing OCR on the mobile or PDA versus a normal computer? What were your struggles last semester when you were actually implementing the system?
we were actually just taking pictures with the phone and then doing all the work on the computer.
Yeah, for
So
what reason?
that was the project requirements.
Yeah. So most of the time, like the machine learning algorithms, they do work on the mobile, but they were really slow, and it takes much longer than on a PC to train your classifiers or to do the machine learning. So the workflow typically is you do use a mobile device as an input. You collect your data using a mobile device. Then you transfer the data to a PC. You do all the machine learning on the more granty side. And then you transfer a model to the mobile phone, and then the classifier actually can work really fast on the mobile phone. So some of the recognition tasks can be handled by the mobile phone once you have the model, but generating the model usually takes too long to run on the phones. Therefore, you usually employ a PC or a server where you have more resources, more RAM, and you can do more computations. So why processing on the phone is slower? What are the contributing factors?
RAM
Yeah,
smaller,
limited amount of memory on the mobile device.
also processor.
Slower processors. Why do we have slower processors?
They say in the papers that they're not using floating points. So I don't know if they're using
That's
now.
not true anymore. Yeah.
Yeah.
So
That's the old one.
yeah, that
Yeah.
was.
Because both of the papers mentioned that.
So the original PDAs, they only had the normal processing units and the logic ALUs without the floating point coprocessors. But the modern CPUs on mobile phones have both. You can do efficient floating point operations. You even have GPUs on the mobile phones. You used not to have that. But why the mobile CPUs are typically slower?
Probably have to say the size and
No?
power consumption probably reduced.
Yep. So it's power consumption and heat generation. So you have to conserve power consumption. You have to conserve power to make the power consumption sort of slow enough that the phone will last at least a day. So the CPUs can't be too grunty, otherwise they will drain the battery too fast. And second, they would get too hot too, right? So if you're consuming a lot of power, that power has to go somewhere. It goes into heat. So you have more problems with heat dissipation on the mobile devices than you have on a PC. It's easier to cool down the processing units. So therefore, phones always will be slightly disadvantaged in terms of power gain with the PCs. But RAM is one of the biggest problems. So we were running a project where we had to teach a classifier based on some samples that we were collecting, and the problem wasn't so much the speed of the CPU, but it was the garbage collector which was kicking in to clean the memory because we were running out of memory every so often, right? So we need to deal with quite a large number of objects, and they were occupying quite a lot of space on the phone memory. Therefore, the garbage collector on the phone was kind of kicking in and slowing everything down to a point where, the training of the data set was taking way too long. So we would have to wait. After every sample, we were doing the update, and we had to wait between 20 to 25 minutes. And on the PC, it was taking between 20 and 30 seconds after each sample was collected. So that was a huge difference because, we couldn't wait that long. So in theory, you could do your learning, your classifying process on the phone itself, but it had kind of a limited practicality. All right, so let's have a short break, 5 minutes break, and then we will talk a little bit about augmented reality and the final paper in the lot.
About the batteries from time.